we are going to continue our discussion on transformations of stress and strain. Okay. Okay, so for this week, we're going to try to finish up the objective number 3. So number 1, we kind of finished number 1. Number 2 and 3, hopefully we can finish it this week. Hopefully also number 4 right here. So this is just more circle using transformation equations, let's say, to calculate for principal stresses, and more circle in order to analyze different types of stresses. Now, before we review our last lecture, I just put this slide so that we are guided with the sign convention we are using for transformation of strain and stress, which are important in terms of calculation. So for example, here, as we mentioned in the class, I just formalize it. I put it on the slide. So we have a tension, which is positive. So we can see, for example, the sigma x right here. It's producing a tension to this square element. So that's a tension. That's a positive number. And whenever we have a compression, we have a negative number, which is this sigma y right here. So that would be a negative number. And this is just a compression along x, compression along y. And if we have shear stresses, so this would be the positive shear direction, and that would be your negative shear. So same thing here. So we have tau xy, tau yx, so which are just paired in order for us to make the system in equilibrium or in equilibrium. Now, okay, so for angles, whenever we have a clockwise rotation, that's a negative number. Our counterclockwise would be our positive rotation for all the cases. And last time what we did is we have this element, we calculated different stresses at various direction, and we found out that it behaves sort of wave if we, for example, analyze what would be the values of, let's say, tau xy, sigma x, and sigma y behaves like this. It follows an equation of a circle. And just to remind you that, for example, for this specific element, this would be the starting point without any rotation. Those are the values. And whenever we substitute in an angle, it could be negative if it's clockwise. This is a positive counterclockwise to our transformation equation. You're going to get these waves, and we can deduce, for example, our maximum in-plane shear stress. So which is this point here. So that would be your in-plane shear stress. That's a maximum value. Or we could also look for theta sub s, which is what kind of rotation do we need for this element in order for us to calculate for maximum shear. In this particular case, it's rotation in a clockwise direction because it's negative at, let's say, 25 or something degrees, or probably 26. Now, if we talk about principal stresses, we are talking about maximum normal stress, which are maximum values for your sigma x and sigma y. So those would be the maximum and minimum values, which we call principal stresses. And this would be the corresponding rotation in order for us to determine what would be the rotation we need. In this case, it's a positive angle. And from theta sub s and theta sub b, we know that, or theta sub s, you can see it, yeah, plus theta sub b would be equal to 45 degrees. So that would be the relationship between the two angles. So now, in the last lecture, what we did is we showed that this sinusoidal behavior behaves like a circle. So it follows a certain equation of a circle. So what we did, okay, I'll just put my notes there. Okay, yeah. So what we did last meeting is, so for example, in order to prove that equations 1 to 3 follows equation of a circle, so we transpose this part of an equation into your left side, use 1 and 3, square all the equation, add them together, and then apply trigonometric relations. So what we got in terms of final equation are the following. Sigma y divided by 2, and that's squared plus tau xy. Just checking if you can see it. Those are primes, those are square, and that's equivalent to sigma x minus sigma y divided by 2 square plus tau xy. So square, sorry. So that's the equation that we got from last time, and we can see from here that this would be an equation of a circle, and how we can tell that. So we know that equation of circle is x, as we mentioned last time, minus h square plus y minus k square is equal to r square. Now, if we look at our equation, so we can tell that this h right here would be this section. We have a k. In this particular case, our k is equal to 0, and this last part of the equation, or the right side of the equation, are equivalent to r square. So which means we can rewrite this equation uh, as follows. So if h is equal to sigma x plus sigma y divided by 2, we can also call it as our average normal stress, which is average between our x and y stresses. Now we can also say that our r, which is the radius of our circle, is equivalent to square root, because that's a square root of sigma x minus sigma y over 2 squared plus tau xy squared. Now, by using this relationship, so we can say that our equation right now, we can simplify it into sigma x prime minus our average stress. So this is just rewriting this equation on the top in terms of some of our assumption there as h and r, and average square plus tau xy, those are primes, square is equal to r square. So that would be our governing equation, or equation of circle, for the equation that we derived from this number 1 and number 3 right here. Now, if we look at this equation, so we can easily say that the center of our circle, which is h, k, is at values average stress and 0. So that would be the location of the center of our circle. And another thing that this equation tells you is that whenever you have a stress and shear, so it follows a certain it follows a circle. So for example, on your left side is a circle. So whenever you have a stress and normal stress and shear stress, it always follows along the equation of the circle like this one. So it's always here. It never goes out to your circle. So now, based on that, we can now plot, let's say, the center of our circle. So in this case, we figured out that HK is our center. It's sigma average and 0, which means that our if we're going to have x and y axis, so two-dimensional, and assume that our x is our sigma x prime, and our y-axis is tau x prime y prime, we can say that the center of the circle is this average stress right here. Now, we know that the stresses follows, or the normal stresses, or normal and shear, follows this circle. If you're going to look at this circle, which one would be your maximum and minimum? And take note, if we talk about principal stresses, we are talking about maximum normal stress, so maximum value and minimum values of our x-axis here, which means that our maximum and minimum is this point right here, that's the maximum, and that would be our minimum point. If we look at this equation here, we can easily say that our maximum, which is this point, is your average stress plus whatever the radius of this circle is. And that's defined by R. So now we can say that our maximum stress, let's call it max for now, would be equal to your average stress, which is the center of your circle, plus r. So that would be this point plus this length right here. How about for your minimum stress? If we're going to use our average right here, it's just your average stress minus r. And then you will get a corresponding value for your x-axis, which is x minimum. So which means my x minimum would be equal to your average normal stress, x and y, minus r, which leaves you the following equation of minimum and maximum, which is also called here as sigma 1 and sigma 2. So I can say that my sigma, let's call it now as sigma 1 and sigma 2. Later on, we are going to establish what is 1 and 2, what's min and max. But for now, let's use 1 and 2 as our maximum and minimum. And that's equal to average stress plus and minus R. Just check, you can see it. Yep, you can still see it. So that would be the equation for principal stresses. And if we extract this information, so sigma 1 and 2 is equal to average, which is x plus sigma y over 2 plus and minus. So plus would be for maximum, minus would be for minimum. And your R value is, if we're going to look for our R value, it would be right here. So that would be your R, which means my R value is now equivalent to square root of sigma x minus sigma y over 2 squared plus tau xy squared. So that would be equation number 4 right there. Now, the fifth equation here tells you what would be the angle of principal stress. So how can we find out the angle of principal stress? So again, let's say you are given with a stress and normal stress and shear stress. If you are given with normal and shear stress, a pair, for example, in an element, again, it would exist along this circle here. But you don't know whether it's principal or not. It could be this point right here. It could be that point. It could be that point, or it could be any other point. Now, the question here is, how would I know what kind of rotation I need in order for me to determine what would be the angle of rotation? Now, this is an important convention that you should know, that if you rotate, so oops, okay, sorry. If you rotate your element by a theta, the rotation in your Mohr circle, or in this coordinate axis, would be 2 theta. So let's say you have an element and you want to know what would be the rotation in, let's say, 15 degrees. So in actual element, using stress transformation equation, it's 15. But if you use this circle, it would mean twice as much, which means you need to rotate it by 2 times whatever angle is. And in this particular case, so let's say you are again given with a random point. It could be, for example, this point right here. So if you perform rotation going into your principal stress, so you want to know how much rotation I need from this point in order for me to reach my principal stresses. So from this point up to that point, what would be the angle? And this angle right here is denoted by 2 theta sub b. So we have 2 theta sub b. And how are we going to determine what would be the corresponding equation for theta sub b? We can just apply the trigonometric function. So you have your radius over here, and this, from this point up to this point, let's say, so for example, this point up to this point, that would be your tau xy, and that would be r. And then you can just play around with whatever you can just play around with trigonometry in order for you to determine this theta. I'm not going to solve it for this one. You can just check it out because we're not going to derive anyway. But that's going to give you this theta, which is tau. 2 theta sub b is equal to tau xy divided by sigma x minus sigma y divided by 2. So that's how this equation was derived. Now, how about your tau maximum in plane? What is tau maximum in plane? You go back to your circle. What's our tau? That's x. That's your y-axis right here. And if you talk about maximum in plane, you're talking about this maximum point here. So the values of your shear stress would not go out of this circle, and the maximum value is this point. And if you check what would be, how can we determine it by just dimensional analysis here? That's just your radius of your circle, which means that my tau maximum in plane, again, we're just doing two-dimensional, you can see that this would be your r. And here you can see that's your r in this equation here. So that's how you will get your tau maximum in plane. Now, another question is, how can I get what kind of rotation I need from one element onto clockwise or counterclockwise in order for me to reach my maximum in-plane shear stress? Because at this point, let's say this is your given, I could rotate clockwise and reach my principal stress. But I want to know what rotation I need in order for me to reach my tau maximum in plane, which is this point. So that would be this rotation here. And you can easily take it out. I'm not going to show it, but you can just play around with your trigonometric function, and then you will find that if you assume that this is 2 theta sub s, and again, we put 2 theta sub s because we know that once we rotate an element in an actual environment, if we put it into this coordinate axis, it would be twice as much. And then once you rotate it going into this direction, and then you apply trigonometric relationship, you will end up with this equation. So that's how these equations were derived. Question before we move to sample problem? Question? So you can see, yeah, go ahead.
Sorry, I just wanted to ask, just a little earlier on, you mentioned about the cracks, the damage, let's say, would be in a more circular pattern, right?
Which one? Which cracks like?
The crack. I'm sort of going back to what you said earlier, that the cracks would be along the circular path, correct?
Oh, sorry, not the crack. Sorry, the stress. So let's
Yes.
say let's say you have this values here. So I'll just clarify that one. So this set of data. So let's say you have stress and you have the corresponding shear stress. So you have two sets of data. You have sigma x and tau xy. And if we assume that our sigma x is our x-axis, this would be our y-axis. If we plot it in x and y coordinate system, all the values will just lie along this circle. So once you, for example, rotate it by 1 degree, 2 degree, or whatever degree you rotate, all the values will just lie on the circle. It's similar to this sinusoidal behavior. Once you rotate this element right here, it will behave just like in a sinusoidal way. Now you can simplify it, put it in XY coordinate system, and that would become a circle. That answers your question?
Yeah, I just wanted to clarify. I thought I misheard something, so I thought I just confirmed.
Okay, that's good.
Thank you.
Yeah, thanks a lot. Yeah. Any other question? Okay, if it's not clear, just let me know. Okay, clear? Okay. And sometimes I would not be able to see your messages, so feel free to interrupt me. Okay, just want to check. Okay. So we are all clear. So we now have all the equation 1 to 7, and now we're ready to solve problem. So let's start with this very simple problem. So for the state of plane stress below, it should be on the right side, to be honest. So determine the principal planes, principal stresses, maximum shear stress, and the corresponding normal stress. But before we answer this, let's clarify what the sample is asking. So let's say determine the principal planes. So this question here asks you how much rotation I would need in terms of theta in order for me to reach my principal planes or principal stresses. So if you look at this element right here, so you have sigma x 50, sigma y negative 10, and you have tau, which is equivalent to 40. Now, one sign that you know that that your stresses are in principle, or your stresses are principal, is that your tau would be equal to 0. In this case, it's a non-zero value, which means that these corresponding stresses are not your principal stresses. And one question is, why do we need to determine the principal stresses? All the designs are based on the maximum stress. So, which means that, let's say you do finite element modeling. So let's say you put a part on a engine, for example, and you want to determine, let's say, what stresses I would, uh, so what type of stresses or how much load it could handle. And those colors in your finite element modeling, so if you see an FEA, those are based on principal stresses or maximum stresses, because that's what matters. Anything below that would not matter at all. You want to determine what would be the maximum stress at that specific point and design your part based on the maximum stress. So that's why you always want to determine what would be the principal stresses. But at the same time, it's not just principal stresses. You also want to rotate it at a certain direction. And why is that? So let's say you have a piece of a plate right here. So let's imagine this is a piece of plate, steel plate. I have lots there, but yeah, it's a little bit heavy. But let's say you have a weld at a certain angle and you apply a load. Once you apply a load, you know the load along this line, and you want to determine how much stress it would give along your weld. So you weld your material. There's a welding, for example, at this direction. You want to know how much pull or how much force or stress you are applying perpendicular to your weld, because that's the weakest spot when you are, for example, manufacturing a certain component. So that's the importance of determining the principal stresses or rotating it at a certain angle. Now let's go back to this. So determine the principal planes, how much rotation I need in order for me to get my principal stresses, maximum and minimum. Letter B is what are the values of those stresses. Letter C is what would be the maximum shearing stress and the corresponding normal stress once you reach your maximum stress. So let's start the problem with letter A. So question is how much rotation I would need. Of course, it's super easy. You can go back to this one and you will find out that, okay, I need to rotate it at theta sub b in order for me to get my principal. I know my tau xy. I know my sigma x. I know my sigma y. I have this equation. I can calculate an angle. It's super easy. But again, I showed you the derivation because sometimes students will just substitute numbers and they don't know how the equation works. It's just, okay, I get a number, but how would I explain those numbers? But yeah, so let's use equation number 5 here, and let's solve the problem. So you are given with, so you first is you want to determine principal planes. So for principal planes, so you're given is, so you want to determine theta sub p. So you're given with sigma y, which is equal to -10 megapascal. So that's in compression. Sigma x, so go to the problem. So sigma x is equal to 50 megapascal. And you have tau xy, which is 40 megapascal. And if you can still remember the equation from the previous slide, so you have tangent to theta sub b is equal to tau xy sigma x minus sigma y divided by 2. And we can easily plug in the numbers. So we have 40, we have 50, so we have minus -10, that becomes plus, divided by 2. And take note that everything is MPA, it will be canceled anyway. So you have tangent, so I'll just calculate it directly. So if you're going to solve this problem, so this one, you are going to get 26.6 degrees. That's a positive number, which means that if we have this this stress state, if we are going to get the equivalent stress at a certain angle, rotation counterclockwise, a positive number by 26.6 degrees, we are going to get our principal stresses. So this would be a positive number, and this would be counterclockwise direction. Now, so that's for letter A, and then we go to letter B.
Excuse me.
Yeah. Right, sorry.
So whenever you did the tan of 2 theta p is equal to the sigma y, shouldn't that be a -10? Not a 0?
It's sorry, yeah, that's true. Yeah, thank you. Yeah, so I forgot about that. Yeah, it should be 10. Yeah, thanks a lot. Yeah, that should be 10. I think my pen didn't work when I wrote 1, but yeah, thanks for pointing out.
No worries.
Or, yeah, or probably I just wrote it 0, but yeah, thanks. Okay. Yeah. So yeah, so take note about these signs because sometimes that's a common mistake in exam. So you can see it's a negative number that becomes a positive right there. But yeah, thanks for pointing out. Okay, so B is the next question is principal stresses. So we want to know the principal stresses, and that would be your sigma 1 and sigma 2 minimum and maximum. Later on, again, we are going to redefine this one. I'm just following the convention in the book, but in the book, normally they use 1 and 2. Later on, they will change it in a way, but let's use 1 and 2 right now. So for principal stresses 1 and 2, so we look at the equation here. That's the equation for sigma 1 and 2. That's stress average. That's the radius of your circle, if you're going to assume a circle there. And then let's just plug in the equation. And if you know the equation, sometimes it doesn't really matter if you know it's a circle or not, but it's good for you to know for sure. So sigma x plus sigma y over 2 plus minus, so that's maximum and minimum, square root of sigma x minus sigma y over 2 squared plus tau xy squared. So what you're going to get here is 50. Okay. 50. So plus, yeah, I think that should be, so that's plus negative 10. So that would be negative 10. I'll just write negative 10 there over 2 plus minus square root of 50 plus 10 over 2 squared plus 40 squared. And what you will get here is sigma 1 and 2. So you have two values. One is plus, one is minus. Something popped on my screen. Just minimize it. It's okay. Yep. Okay. And then you will end up with negative 30, which would be your minimum stress, and your maximum stress would be 70 megapascals. You can check it if you want to make sure everything is all right. So that would be the answer to letter B. What would be the principal stresses? The next question here is what would be the maximum just checking. Okay. Yep. I have a note there, but I don't have any calculation. But yeah, anyway, so the next question here is what would be the maximum shearing stress? So which is tau max in plane. So we want to determine what would be the maximum in plane shear stress. And if we look back at the equation here, this would be your equation number 6. So just have to get the radius of this circle, which is square root of this quantity here. So which means I could easily calculate the numbers because I'm given with those numbers. So, okay, so tau max in plane is equal to sigma x minus sigma y over 2 and it's square plus tau xy square root. You'll end up with square root of 50 plus 10 over 2 square plus 40 square, and then you will end up with, and don't forget your units when you write the final number. I'm used to just writing everything without the units, but eventually you have to make it right. So you have 250 megapascals. So that would be the maximum in plane shear stress. And the question here is, now we know that if we have this position of a stress state, we get the rotation at a certain angle, which is theta sub p. In order to get our principal stresses, we get our maximum shearing stress, which is not associated with theta sub p. Take note that your principal stresses is associated with theta sub p, but your tau max is not. So how can you determine what would be the corresponding normal stress if we reach the maximum shearing stress? So again, these are different things. One is principal normal stress. Another thing, it's a different rotation. It's a maximum shearing stress, and they are 45 degrees apart in terms of angle, but you can easily calculate it in terms of equation. So let's find that. So we need our normal stress, which are associated with the tau max in plane. Again, if you talk about principal stresses, your tau is always 0. It's not the maximum. So you need a different rotation in order for you to get your maximum. And that's defined by theta sub s. So how can we determine theta sub s? We look back at the equation and then we see, oh, we have theta sub s at number 7. And then we can use theta sub s there. So we have tangent to theta sub s is equal to negative sigma x minus sigma y over 2. Then we have tau xy. So we have sigma x and sigma y, and then we can just plug in those numbers. So 50, and this one we're going to change to plus. Oops, I forgot again. So plus 10. So yeah, probably the last time it's my bad. So yeah, okay. So 40. And then you will get theta sub s is equal to negative 18.43 degrees. So this would mean that if we go back to this problem, so I have this, so just imagine I have a box here that refers to elements. So let's say that those stresses are applied to horizontal and perpendicular lines. So I will rotate it. I'm just checking which one is clockwise in your end. So this rotation, I cannot figure out which rotation, but anyway, in order for you to get your principal stresses, you have to rotate counterclockwise in order for you to get your principal stresses. And if you go back again to your 0 position, in order for you to get your maximum shear stress, you have to rotate clockwise because it's negative. So if you rotate, that would be the condition wherein you will get your maximum shear stress. But that's not the question. The question is what would be the corresponding normal stress. And we calculated the angle. It's because we want to determine what rotation we need. And at the same time, we can plug in that angle to this transformation equation in 1 and 2. Take note that this is a general transformation equation at any rotation angle. So since we already know what rotation we need in order for us to get our maximum in-plane shear stress, we can just plug in theta sub s here, plug it in here, and then we are going to get our normal stresses. Now, you might ask a question that, yeah, I can just plug in my theta sub p to that equation, and I can get my principal stresses. And that's correct, but we just have a special equation there so that life will be simpler without dealing with our theta, because normally your principal stresses are much more important. So that's why you have a more simplified equation here. But now let's look at this number 7. We have theta sub s. We have to substitute it to equation 1 and 2 in this slide. So if we do that, what we're going to get are the following. So not going to rewrite the equation here, but take note that this is sigma x prime is equal to whatever number is this one. And if you calculate that one, that would be 40. Okay. I'll give you some homework to substitute theta sub s negative 18.43 right at home. If you substitute it this one, you will get the following. So I'm not calculating it for now so that you can have a little bit of practice, but what you will get are the following: 20 megapascals, and this would be 20 megapascals. So substitute this angle to your equations 1 and 2. So, but you also have the same sigma x, sigma y based on the given, and you will end up with the following: Now take note that your sigma x and sigma y at your tau maximum in plane, they are the same. And if we go back again to this plot, we mentioned that before, that once we reach a rotation wherein we achieve the maximum in plane, we are going to get normal stress x and y which are equal at this point. So it's just telling you that once you rotate or you get the equivalent stress at the rotation angle going into your maximum in plane shear stress, your normal stresses would be equal, and that's the case right here when we solve that problem. Any question, or is it confusing when I explain it? Just let me know if it's confusing. It's important for you to grasp all the details because sometimes there's a problem that you need to analyze the situation rather than just substituting the numbers. Question?
Yes. When it
Yep.
comes to finding the normal stresses at the maximum shear state,
Okay.
can
Yep.
we not just do sigma x plus sigma y divided by 2 to find that like average stress?
You can, yeah. Technically, yeah, you can, yeah. Based on the numbers, that should work because so take note that so yeah, that's a good point. I never explained that. I mentioned the long way, but that's correct. So we have sigma y is equal to sigma x prime plus sigma y prime. This will always be true at any rotation angle, which means that if you have the same um, x prime and y prime, that's just your average. But yeah, that's correct. Yep. Yep. That answers your question.
Yeah, that's perfect. Thank you.
Okay. Yeah, but that's correct. So I never pointed this one out, which I will, I think, eventually. But yeah, but thanks for letting me know. A question? Okay, so let's move on to the next one. So now, those are a very easy analysis in terms of getting principal stresses. What would be the rotation to get, let's say, your normal and maximum in plane shear. But let's take a look at for example, let's not look at this one. Let's look at this one right here. So this would become a more complex problem if we, for example, consider a three-dimensional problem wherein we are asked to, for example, analyze what would be, for example, the stresses, principal stresses at point H, or what would be the maximum in plane shear stress. So that becomes a problem when we go to 2D problem, but 3D problem. But before we discuss that, let's discuss what is a force couple system. Now, if you have a system like this one, so let's say you are asked to determine what would be the stresses at point A. So for now, let's just imagine two-dimensional. So you have a force, 40 newtons, you have 60 newtons here, 50 newtons here, and then you have a moment, which is 100 Newton per meter. So you're asked to determine stresses at point A. You can transfer all those stresses at point A by using a force couple system. And how can I transfer this 40 kilonewtons to A, or this 60 newtons to A again, and this 50 to A, in order for me to get a point and analyze the stresses? Because that's what we are doing. We're taking a point, analyzing the stresses. In this case, the forces are applied like on various at various locations. So first, let's have our point A. So if you have a moment in your system, for example, like this one, I can easily transfer this moment at point A. So this, for example, 100 newtons per meter, I could easily move it to this point. So it's not a problem. So I can put that specific moment, 100 Newton meter at point A. Now, how about the forces? The forces needs a moment in order for you to move it from one point to other. So let's say if we are going to move this 50 newtons to point A, what would be the effect of this 50 newtons at point A? You have to get the moment. So if you check the moment, so from point A going to 50, the rotation is clockwise. So this 50 newtons creates a moment which is equivalent to 1.5 times 50. And that moment is clockwise. So which means it's clockwise like this, and then it's by 50 times 1.5. That gives you 75 Newton meter. Now, once I deduce the moment that it creates, I can now put this 50 newtons to my point A. So I can now transfer my point A. So this is what we call the force couple system. So I can put now my 50 newtons applied to my point A. Now, I have 100 newtons here. I have 75. So in effect, it will cancel out the effect of 75. So that will give me, so I have a point A, I have a force which is 50 newtons, let's say, and then I have a moment which is now 25 newtons per meter. So why 25? It's just because I have 100 here, I have 75, so 100 countered by 75, so there a remaining moment of 25 in your counterclockwise direction. So, but now we are okay with 50 newtons, we are okay with 100 newtons per meter. How about 40 and 60? So we can apply the same. So for example, at point A, so it's 0.5 times 40. So it creates a moment which is clockwise. So it creates a moment. I'll change color, clockwise, which is equivalent to 40 times 0.5. Times 0.5, and that would give you 20 newtons per meter. Now, if I'm going to get, again, my 60 newtons, that's 2 times 60, so that's also clockwise. So that would give me another rotation for clockwise, which is, which is 60 times 2. That gives me, 120 Newton meter. Now I can add this too because they are in the same direction. So I can have 140, and then if I have a 25, which is in the counterclockwise direction, I will end up with, so eventually this will end up with a moment which has a direction clockwise at 115 Newton per meter. Or you can call it negative because negative is clockwise for moment, but let's just put it 115 clockwise, and I have my force, which is 50 newtons. And now I can transfer this 40 and 60 to my point A. So I'm going to have 100 pointing down. So I have 100 newtons here. So that would be my final, that would be my stress state at this specific point. Now, the question here is, how can I apply it, stress transformation here? Not yet, because this is just showing you in two-dimensional how it works, but this type of force couple system would work perfectly if you have three-dimensional. So this would be the force couple system of this figure on the left side. So you can have a force along X, for example, 50 newtons, along Y, 100 newtons, and then you have 115 in terms of moment. And why do I need to determine the moment? Because initially, we are just talking about normal stresses, shear stresses. So why do I have a moment there? Your moment, most of the time, can also produce either normal or shear stresses, which we are going to talk about in this problem. We are not going to solve it right now because we only have 6 minutes, but I'm going to explain you how are we going to do the stress state at point H by looking at different stresses. In this case, I have P, and then I'll produce a moment at a certain, let's say, axis, or rotation at a certain axis. But let's first read the problem. So now, a singular horizontal force P, which this one here, with a magnitude of 150 pounds, so that's 150 pounds, is applied to the end D of lever ABD. So your lever is A, B, and D. Knowing that portion AB of the lever has a diameter of 1.2 inches, so the diameter at this point is 1.2. Determine the normal and shearing stress located at point H. So which is point H here. And having sides parallel to the X and Y axis. So why do we need to take note of this axis? Most of the time, if you read books, sometimes you make mistakes because the book doesn't tell you which one would be the reference planes. And in my case, whenever I give you a problem, I'm going to put what would be the reference plane. It's just some books will have a fixed reference planes for all the problems, but they're not going to mention you, okay, what would be the reference plane. But in this case, our reference plane is X and Y. So this would be the Y and X. What do I mean by reference plane? So if you are looking at this point H, you are, just imagine you are sitting in front of this H, and then you are looking perpendicular to plane Y and X. So you are sitting here, you are looking at H, and then just imagine that you are there, you are looking at the box, this would be your H. So I'm looking at this square right here, and then I'm checking, okay, what would be the stresses along X, along Y, what would be the shearing stress? So that would be the importance of your reference plane. And that would be the principal planes and principal stresses at point H, which means that once I get my stress state at point H, for example, what's the principal stresses? Because once I get the stresses at that point, it's either aligned along X, along Y. I have my shear, but the thing is that your principal stresses? Most of the time, the answer is no, because you're going to get shear, for example. But anyway, so now, determine the principal planes and principal stresses at point H. Now you are facing at this point. Now, before we discuss this, let's first find the effect of P. Again, going back to force couple system, our objective is to transfer this force P to your point H. That's the concept of a force couple system. So for example, I can get whatever moment it would produce along whatever axis, and then I'll transfer it at H because I want to know what would be the stresses at point H. Okay, let's do this one. So if we are going to so you have to do it plane by plane in order for you to analyze what would be the rotation. So let's say if you look at plane Z and X, so this would be X and Z. So you are looking from the top. If you are looking from the top and assuming that you have a point just in the middle of this section, just imagine you are in the middle of the section. You are looking at P. So if you are facing at the top, you would imagine your P produces a moment, or it's a torque in this case, but it produces a rotation along your Y. It's correct, right? So now you are looking from top. So from top, you are facing, you are located on the top here, and then you are facing down. And then what you see is plane XZ. And from your view at 100, so I'm going to write it here. So you're looking down here. So let's say that would be your Z, that's your X. So the direction pointing towards you would be Y. So you're looking down. If you're looking down, you will see that if this would be your point D, you have a P right there. And you have 18 inches there. So it would produce a moment, but in this case, you have a section. So you are producing a torque along this section here. Now that's just one plane, so you have to look at different planes in order for you to assess what would be the rotation or moments that it would produce at different directions. So now you're looking from top. Let's imagine you are looking at X. So you are here. So you are facing this section Y. So you're facing here. So you are looking at plane Y and X. So if you are going to draw, what would be your view? So I'm sorry. So, okay. So any question, class? Normally during in-person, this is the most confusing thing that students ask about what rotation. But yeah, you have to look at first Y, and then now you switch to X. Now, when you are at this point, you are looking towards this plane, which is Y and Z. And if you're looking at this one, your P is pointing this way. So that will be your P. So now we are analyzing it in 2D step by step or at each phase. So this P right here produces a moment, this rotation. You have a distance from this point up to that point, which is 10. So this distance would be 10. So it produces a moment 10 times P, which is rotation along your x-axis. So you would imagine that this P produces a moment along our x-axis. Question? And now if you move to your Z, so you're now sitting at Z looking at YX, you will see that it will not produce a moment at Z because your P, you will not view it at this point. It's just a point facing towards your plane. So it will not produce a moment along Z. So those analysis, we're going to continue next meeting because it's 2:20. But I hope I made a kind of introduction in using transformation of stress and strain in 3-dimensional. So that's just one. We apply a force couple system, and then we're going to deduce what would be the stresses at point H on Wednesday. Question at this point? Going to stop the recording. Question sheet. Yes, yeah, you'll be allowed. For your exam, I'll just stop the recording.